overall, I think this test is going to probably worry a lot of you when you get your marks back. And I don't want you to be too afraid. Your marks might be lower than you expected, but the test itself is quite a challenging one, particularly with question 3. I think with question 4, you hadn't really looked at the way to deal with that. In today's class, you probably got this right. Just with the multiple choice questions, in terms of mechanisms, both answers, A was the incorrect mechanism. With the first question, it really should be one of those things when you look at the mechanism that's been drawn here, it should really just say to you, no. It cannot, what's happening here cannot be happening. It's a complete wrong movement of electrons. All the other movements of electrons, though maybe you haven't seen them before, are completely rational in terms of a negative charge moving to a place that can accept electrons, and bonds can break. Question 2 was a little bit more tricky in terms of the mechanisms, but it's this one over here which is wrong. Although it seems logical that a minus can go to a plus, we need to remember that a nitrogen with a plus on it is not an electrophile. It cannot accept electrons. To do that, it would have to kick out an H minus, and that's completely impossible. This question over here, we had to say, give at least 2 things that were wrong with this planned synthesis. I found this very difficult to actually mark. A lot of you made certain points which, while they were true, were not really the obvious things that were wrong with this question. So let me deal with the obvious things wrong first and then deal with some of your questions. The standout issues over why this is not going to work, first and foremostly, is the use of a tertiary alkyl halide. This is a useless, absolutely useless electrophile for a nucleophilic SN2 type of reaction. And so wanting to do an enolate reaction on this is totally impossible. It's not going to work. The other thing that stands out is the use of sodium hydroxide. When you have an ester like that, sodium hydroxide is going to hydrolyze that ester, and we're going to end up with the carboxylate. Because it's, if you follow the mechanism, you're going to see that you're just going to get the carboxylate being formed, not the carboxylic acid. So that's completely useless. Now, a lot of you answered that sodium hydroxide is too weak a base to form the enolate in order to go forward. And that is true. It is too weak a base. But the bigger problem is the fact that it's going to hydrolyze. Some of you would have said, well, we should have used sodium methoxide because then we wouldn't hydrolyze it. And others of you actually pointed out, well, sodium methoxide is also not a good idea because even though the sodium methoxide will form the enolate, enolates weakly generated using like methoxide on esters allow for cross condensation to occur, the Claisen reaction. We haven't done the Claisen reaction yet, but it is a possibility. So actually, if you wanted to do this reaction, and the question was not, you didn't have to give reasons how you would do the reaction properly. The best way to do this, as we've just learned, if you're wanting this product here, would be using a silyl enol ether type of method. All right. In this question, most of you were very good, and you recognized that this is clearly the bond that's going to be formed in this reaction from this starting material to this product, and that the reagent that we're going to use would be something like allyl bromide. And that was good. If you said the allyl bromide, you would have got a mark for that. The problem in this reaction, though, is that we cannot form an enolate of an aldehyde, so we can't use LDA, we can't use any other base in order to deprotonate there, form an enolate to react with this electrophile over there. It would be nice to be able to do that, but it's completely theoretical. In practice, it's a real problem because of how electrophilic and aldehydes are, and they're going to self-condense. And you're going to see that when we start dealing with the aldol reaction. But for now, the way to do this is, particularly when you've got an active electrophile like this, is to use an enamine. So we want a secondary amine. The pyrrolidine is a very good option, don't forget that we need some acid present as well. All right, the acid is important in that. And then the second step is that we will add our alkylating agent. And then the third step, because we follow through on the mechanism, we're going to see that at the end we're going to be left with this iminium, or can go back to the enamine, and so we need to hydrolyze that to take it back to the aldehyde, and so H3O pluses, some sort of acid workup is going to be needed, and that would have given you your marks. Just remember, I gave the wrong marks for these questions. This one was only worth 3 marks. This one was worth 3 marks. And this one was, the multiple choice was 4 marks in total, 2 each. If you had negative marking, you would never have got, the least you would have got would have been 0 out of 4. I wouldn't have, if you had like a -1 and taken off the other questions. All right.